Thank you to the organizers for putting this nice workshop together. I'm going to talk about some fairly simple examples around the exponential period conjecture, which is an extension of the classical period conjecture that Annette is explaining right at the moment. So all of it is now the joint work with Javier Frezan, work in progress. What it's neither really work nor is there a lot of progress. So that's the common joke. So it's conversations with Javier Frezan. My mise en place for exponential periods is always like this. Okay, inside the complex numbers is some number field. And then I need some algebraic variety over K. Usually I will also choose some closed subvariety inside X. And then what makes the periods exponential periods is the choice of a regular function on X. So you can think of it as a map, a morphism of varieties from X to A1, or the global section of OX, or whichever you like. So with these things, we may cook up some singular cohomology groups, some theorem cohomology groups, and all the incarnations together, we would call this an exponential motif. I'm using this just as a symbol, so something that is the Hn of X, Y, and F. So one incarnation of this M would be some theorem cohomology, which is going to turn out as a finite dimensional K vector space, or there is a singular cohomology within this, which in this instance is called rapid decay cohomology, associated with X, Y, and F. And this is so rapid decay. And this is going to turn out as a Q vector space of the same dimension. And now it's time for examples. So my first choice for a variety is the affine line with the origin removed, spec K X inverse. We have seen it this morning. As a closed subvariety, I'm deciding here to choose a single point, the point 1. And as a function, I just take the coordinate. So as a Laurent polynomial, or as a morphism to the affine line. And then with all of this, I have H1, X, Y, and Y. And just the collection of this data is what I'm calling right now the exponential motif H1, X, Y, F. So with this should now come a theorem realization, so some theorem cohomology, and some singular, as you saw also already in Javier's talk, rapid decay cohomology. So in this case, what is it? The theorem complex is really simple. So it goes from K, X inverse. That's the a structural ring of X to k x inverse dx. Here is the differential d, but I'm not going to use the standard differential here. It's the function f that is going to twist the differential a little bit, and which makes out of the classical theorem cohomology for h, x, and y, the theorem cohomology for the triple x, y, f. So here, the differential is doing the following. It sends a Laurent polynomial h to h prime dx. That would be the standard differential. And now I'm putting here minus f prime times h. Voila. This is my theorem complex. The cohomology in degree 1, this is just the co-kernel of this differential. Co-kernel of the differential. And no, I haven't. No, the y, it comes. It comes. Just leave me alone. So this map is injective, and the co-kernel is two-dimensional, and I leave it up to you to check that the co-kernel is generated by the symbols dx over x and dx. Right, that's the co-kernel. And I'm telling you, this is the theorem cohomology in this instance. So, as a k-vector space, it's two-dimensional. All right, that's the theorem side. Let's go to the rapid decay side. The topology of the situation is this. So here's the complex plane with the origin removed. I have marked one point, which is here. And I have this function f of x, which takes a large real part when the x is far to the right. So here, far right. And what we are allowed now is topological cycles that are either honest topological cycles, loops on the topological space, closed loops with no boundary, or paths that do have a boundary, which is contained either in y or somewhere at infinity in a direction where the real part of f grows to infinity. So I have here this cycle, and I have another one, which is a path that goes from 1 vaguely to plus infinity. H1 rapid decay of x, y, and f. That is the vector space, the Q vector space, generated by the cycles sigma naught and sigma dash, but it's actually the dual vector space of that. So here, these two cycles, they represent a basis of singular homology, and the cohomology is the dual. Okay, so that is what the RAM and rapid decay is in a simple example. And now we do the same thing that we do classically. So we pair the RAM and singular homology classes to complex numbers using an integral. So there is now a well, let's call it integral pairing. Which I can see as some map between V and W and V dual and goes to the complex numbers, given by integrating a differential form along a topological cycle, or you can see it as an isomorphism of vector spaces, then it's called the period isomorphism. And this is an isomorphism that goes from W complexified to V complexified. It's defined over the complex numbers, alpha. Well, I say it's an isomorphism. That's not an easy thing to verify. So this period pairing is actually a non-degenerate pairing, and the induced map is indeed an isomorphism. So in the example, well, we have two choices for a path and two choices for a differential form. We get a 4x4 matrix of complex numbers, which is the matrix of this integral pairing, and then it depends how you choose your basis and dual basis. It is also the matrix of the period isomorphism. Here it is. So I can do dx over x or just dx. I can integrate around the origin or from 1 to infinity. Here, that is simple. So integrating around the loop, integrate an entire function gives you 0. Integrating dx over x gives you 2 pi I. And I should have of course written this integral somewhere. Let's do it here. So the integral I'm looking is the integral over some cycle e to the minus f against the differential form omega. So the whole thing becomes interesting because of the presence of this exponential here, and that's why I'm allowed to choose cycles that go somewhere where the real part of f goes to infinity, which makes this thing here nicely converge. So there is this integral along the line, so which would be e to the minus x dx integrated from 1 to infinity. That's also not hard. This gives you e inverse. And then there is this one here left. That would be the integral from 1 to infinity e to the minus f. F is x, omega. Omega is dx over x. So what is this number? Either you know or you ask a computer, and it will spit you out that this is the value at 1 of the exponential integral function, which is pretty much a tautology this way. So let's see what are the properties of this exponential integral function. So it's a classical thing, of course. E1 of z is the integral and goes from 1 to infinity e to the minus zx dx over x. That's one way of writing it. We can give it a maybe better recognizable expression. So this is minus log z plus the Euler constant gamma minus a power series. N goes from 1 to infinity minus 1 to the n z power n, n times n factorial. So wow, now we have something that has these log factors. There is the Euler constant there. There is no other period numbers, and here there is an E function. So this is precisely a pretty special case though, but precisely the structure that Javier was talking about this morning. I can also give you an asymptotic expansion of the same function at infinity. So equality is maybe not what I want to say, but it's asymptotic to e to the minus z power series now that goes from 0 to infinity minus 1 to the n times n factorial times z to the minus n minus 1. And here, this part is an a function. And, well, you see here, of course, this is a power series with a 0 radius of convergence. This sign here, it means that if you take the difference between E1 of z and some truncation of this power series, that the difference in absolute value goes to 0 with order O to the next higher term. That's what an asymptotic expansion means here. So E1 of 1, you can see it as a special value of an E function with some pollution, or you can interpret it as a special value of an A function too with a little pollution. So that's that number here. Numerically, it's about 0.21 something. Good. So here, E1 of 1. And we are asking now, what can we say about the transcendence or algebraicity nature of these three numbers that are here? And that's something the period conjecture predicts. So in general, what we have, there is an algebraic subgroup inside the GLV, which is, in a sense, the largest algebraic subgroup that commutes with all the symmetries of the motif. So for those who know, it's a Tannakian fundamental group. It's the Tannakian group of M in the Tannakian category of exponential motifs. But here, let's just say it's some linear subgroup, and whenever, for example, I find some submotif of M, this subgroup has to stabilize the corresponding linear subspace of V. If the motif M has some automorphism, the group G must commute with that automorphism, or endomorphism, or whatever. So there's the motivic fundamental group. Then, this fundamental group, it acts on the isomorphisms from W to V just by postcomposition. So G, what I will do now, base change K acts on isomorphisms from W to V base change K. So that is, this is like a GL something over K. It acts on here by just composing. And alpha, this isomorphism between the complexified spaces, well, that is a complex point of this variety. So alpha is a point, well, defined over C here. So as such, it has a Zariski closure. And this Zariski closure of alpha, it's a closed K subvariety of this affine variety of isomorphisms. And the conjecture is this. It is that this Zariski closure of alpha is a G-torsor, or if you want, is a principal homogeneous GK space. GK acts simply transitively on this K variety. So once you pick any K point, the two varieties G base change to K, and this Zariski closure just become isomorphic. This Zariski closure, we can describe it. Actually, it is the spectrum of K adjoint all entries of a matrix for alpha and the inverse of the determinant. So you pick, maybe it's easiest to see here, you pick a basis, a K basis of W, you pick a Q basis of V. Via the integral pairing, you get a square matrix of complex numbers. Well, this matrix. So we adjoin to the field K all the entries of this matrix and the inverse of the determinant, and the spec of this should be a principal homogeneous space under a group, which is the motivic fundamental group of K, of M base change to K. So what does it do in this case here? Well, from the shape here, you guess already that the group G is going to be something vaguely upper triangular. At least I chose my basis for the RAM and the singular cohomology in a way that puts this somehow suggestively forward. So indeed, I have here my motif, which is H1 XYF, and I can send it to H1 just X and F. So there's a map that sends the identity by the identity, X goes to X, the empty subset, which I didn't write here, goes to Y, F goes to F. That's a perfectly fine morphism of triples XYF and XMTF. So it must induce something on the motifs, if you want, on the theorem cohomology, on the singular homology, and so on. And there's a kernel, which is H0 of Y and F restricted to Y. And now it turns out that this is just a short exact sequence. In singular homology, so here I had cycles sigma naught and sigma bar. In homology, the sigma naught comes from here. And this is a boundary map. So the cycles here go to their boundary. Sigma naught has no boundary, but sigma bar has a boundary, which is just the set, only one. This is Y. So here, this is actually a very easy motif. It's just H0 of a point with a function, and the function is the constant one. So I would write this motif as E1. In general, I will say E alpha is H naught, the point, and the constant alpha for a function. So these motifs are pretty easy to understand. E alpha plus beta is E alpha tensor E beta. And that should remind you of exponential alpha plus beta is exponential alpha times exponential beta. This motif here is also easy to understand. That is just q minus 1 is the h1 of Gn. So this shows that M is an extension of something of dimension 1 by something else of dimension 1. My basis for the singular homology was chosen compatible with this extension already. So the motivic Galois group has to respect, it has to globally fix, say, this subspace here inside the motif, which tells you that with respect to this basis, the motivic Galois group is going to be upper triangular. G is contained in the group of upper triangular matrices. So its dimension is at most 3. On the other hand, you can show, or at least believe me, that E1 to the power A is isomorphic to Q1 to the power B if and only if A is B is 0. So these two motifs live in a very orthogonal world, so that will tell you that the diagonals are inside G, and the whole question is really whether G is all the upper triangular matrices or just all the diagonal matrices. So you have to decide this somehow, and the way to decide such a thing is always the following. So no matter what your motif is, if you take any of its realizations, then the Tanakian group of this realization is contained in the motivic fundamental group. So if I say any realization, you might classically think of a Hodge realization, of a Tate Galois representation realization. These things, they have fundamental groups like a Hodge group or the image of a Galois group. And these groups for the realizations, they're always contained in the motivic fundamental group. The realization I'm going to look at here now, since it's the theme of the conference, is a differential realization. So with this motif, this situation H1 x, y, f, I'm going to associate now a differential module. The differential module will have a Galois group, a differential Galois group, and this differential Galois group will sit inside the motivic Galois group. So from like this symmetry, I gave a sort of an upper bound for the Galois group. From the differential side, I will find the lower bound, and the two will just squeeze together. So I will have determined the actual motivic fundamental group. So how to make a differential module out of M is not difficult. We have seen it already in some instances. We take the function and just replace the function f with z times f for a formal complex parameter that is supposed to live somewhere in the complex plane close to 1. Out of f, make zf, leave everything else how it is. So we get, instead of numbers in the period pairing, we get functions of the formal parameter z. So the integrals we are looking at now is the integral over sigma e to the minus zf against omega. And we get a matrix of functions, still sigma naught, sigma line, dx over x and dx. Nothing changes here, but if we change the x to zx, well, we get the actual exponential integral function as a exponential period function here. And here we find 1 over z e to the minus z as the other integral. Okay, so that's now a matrix of functions, and it turns out that this matrix of function is a matrix of solutions of a differential module. I can give you the differential module in the form of a matrix equation. d dz f1 f2 is 0 minus 1 0 minus z is 1 over z. So here it is. This is the matrix differential equation, and you can check. You plug in the vector 2 pi I 0 into this system, it solves it. Or you plug in the vector exponential integral and 1 over z e to the minus z in this system, and it solves it also. The determinant is non-zero. Boom, fundamental matrix. Picard-Vessier extension is the algebra generated by these three functions and the inverse of the determinant. The differential Galois group. Maybe I give you also the operator. I put it somewhere. Yeah, if you want, the single differential equation is d minus 1 plus z over z d. That is the differential operator. It lives here. Yeah, me too. So you see, it's a product. This is precisely one of the, I don't know how many it were, 12 conditions, equivalent conditions in a theorem we saw this morning. So it tells you that the differential Galois group cannot be SL2 or cannot contain SL2, that's it. And well, sure, it's an extension of the differential module associated just with the differential operator del, whose solutions are constants. Voila. And the differential operator, which is here, whose solutions are this function. Now, question is the extension trivial or not? Well, it's not, and you can see this in a number of different ways. One is maybe just to look at the behavior of these functions around zero. So E1 of z has some monodromy around zero, and it cannot be polynomially dependent on this function here, which is meromorphic around zero. So the differential Galois group is in the same basis this group here. So the group where you are allowed any non-zero entry up here and any entry up here and any non-zero entry down here. So there's a linear algebraic group over Q, and it's contained in G. And now we conclude that the group G is actually the full group of upper triangular matrices. Its dimension is 3. So if back here, if the Zariski closure of alpha really is a principal homogeneous space under G, the dimension of the Zariski closure of alpha is 3. So that would say that the transcendence degree of all entries of the matrix and its inverse and the inverse of its determinant, the transcendence degree is the same as the dimension of the group. So the exponential period conjecture predicts now that 2 pi I E1 of 1 and E inverse are algebraically independent numbers. In particular, popular conjecture, pi and e are algebraically independent. End of example 1. So now you can play with this by choosing for x the variety of your choice, y the way it is set up here. The problem is, as soon as the x becomes vaguely more complicated, you cannot do a lot of well, you should speak for myself. So I cannot do really any very explicit calculations. So I have one more example where I can do actually something fairly explicit. And this time, x is just going to be the affine line. Y, on the other hand, I allow any number of points, so n points. And for f, I'm going to take the function x squared. Again, now there is a theorem vector space, there is a singular vector space, and I can write down an integral pairing. So let me give you a theorem. Here, the theorem realization of the motif still h1 x y f is given by the differential form just dx. And then what I will do is I will write down something which is not actually a differential form. So it's a Dirac delta at a1, Dirac delta at a up to an. So that's an n-dimensional k-vector space. So why do these things here appear and which are not really differential forms? Well, now it's what Annette was asking. So now I really have to talk about the theorem cohomology, not just of x, but of a pair xy. If y is just one point, that kind of works sometimes without the deltas, but here I really need this. So that's the theorem cohomology. And the singular, or rapid decay, I will make the picture. So this time, the real part is large. The real part of f is large when x is real and negative, somewhere in that direction, and also here. And in between, I have these points that are marked. Let's say here is the point hij. And now there is no loops that are not contractible, but I have plenty of paths that start and end somewhere in a colored region. So there is still this path that goes, let's say sigma infinity, this is the real line, it goes from minus infinity to infinity. And then what I can also do, I can start somewhere at minus infinity and end up at one of my chosen points. Call this maybe sigma I. And here is my basis for the rapid decay homology. So it's sigma infinity, and then sigma 1 up to sigma n. And I can integrate a form against the cycle. I will do the integration directly with the parameter z. So I'm integrating on a cycle e to the minus zf, that's x squared, and then dx or delta. And delta just means evaluation at the point. That's how the Dirac deltas work. So to make this nice and suggestive, I put here dx, maybe delta a1, delta an, and then here let's start with sigma infinity, sigma 1 up to sigma n, and it looks somehow better if I subtract half of sigma infinity from each of these. That is just for cosmetics. Good. So what will I find here? Well, that is precise. So here this entry, that's precisely this integral from minus infinity to infinity. So this gives me square root of pi divided by square root of z. Then this path doesn't meet any of the points, or you can move it away from them anyhow. So there is nothing to evaluate. I get a column of zeros. Then let's go down here first. So I have the evaluation at one of these points, aj's, of sigma I and then minus half sigma infinity. So if I is different from j, I just get nothing because this path here doesn't meet the other point, or you can move it away from it. So this gives you here a diagonal matrix, and the entries are going to be e to the minus a1 square z, e to the minus an square z, and nothing else. And now the interesting part is the integral that goes from 0 to, say, a, e to the minus zx squared dx. So that's essentially very close to the definition of the error function. So let me put this on my special function side. As a reminder, the error function of z, it is defined as 2 over square root of pi. That's a normalization the statisticians like to make. And then it's the integral that goes from 0 to z e to the minus y square dy. It is 2 over square root of pi. There's a power series representation, minus 1 to the n, z to the 2n plus 1, 2n plus 1 times n factorial. And this is not quite, but close enough to an e function. So here, what I find is, as a period integrals, square root of pi over 2 square root of z, error function of a1 square root of z, and so on. These are these numbers. Now, it doesn't look like it, but here, as a function of z, that is actually an e function. It's an honest e function, because you see here, first I divide the, so let's say I replace z by square root of z, then I get here the variable to the power n plus a half, and then I take out this z to the power 1/2, and I get the nice power series the way I want it. So this is my matrix of period functions already. And just as before, the differential Galois group associated with this matrix is contained in the motivic fundamental group. So in the motivic fundamental group, we probably find the GM copy here because of the presence of the pi. So there is, again, a Tate twist. And then we will find a Galois group that looks more or less like this, suggestively. So here it is how it actually looks like. There's, again, a short exact sequence, just like the one that is up there. F is x squared. All right. So this is my motif. This is again a boundary map. As before, here now I have the h0 on the finitely many points with the function x squared. So that is just a direct sum E of aj squared. So it's finitely many points. Here's my motif, and this is an interesting guy. We tend to call it Q1/2 because its period is square root of pi. So if I get tensor product it with itself, I should say -1/2, because if you tensor square it with itself, you get the pi, which is almost like the Q -1, at least if the base field contains a square root of -1. So already that you have this direct sum here tells you that the motivic fundamental group also is going to be a torus thing. Here you get, for the motivic fundamental group, a GM copy. And, well, then there is again the question of the extension. So your motivic Galois group will have a shape that looks just like something the period matrix suggests. Let's say the differential Galois group is in this case ±1. So up here you find the finite Galois group of the square root of z. It's an algebraic piece. Then down here you get a torus T1, Tn. I'll tell you what it is. And up here, you get a vector group, I call U, and it's the unipotent radical of the Galois group. So the torus down here is all the T1 up to Tn with the following property. It is that T1 to the power K1 ... Tn to the power Kn is equal to 1 if K1 A1 square plus Kn An square is equal to 0. So whenever you have a z-linear combination of A1 square up to An square, then this z-linear combination imposes a multiplicative relation on the characters of the torus. You can say also that T is the torus dual to the group generated by A1 square up to An square. So its dimension is exactly the rank of this group. U, now a little bit of group theory, is also not hard to identify. U is U1 up to Un, with the following property. Ui is 0 if ai is 0, and ui is equal to uj if ai square is equal to aj square. So that's a little group theory that you can play. You see, for example, that this torus T, by conjugation, it acts on U. So there's not so many subspaces of U that, not so many subspaces up here that come into question for U. It has to be stable under the action of T. So for example, if T is the full torus, then the only possibility for you is you can choose to take a coordinate or not. So here, this is the answer for the differential Galois group. Now, for the motivic Galois group, you can choose anything here. And the period conjecture, let me finish with this. The transcendence degree of k adjoint, well, square root of pi, e to the minus a1 square, e to the minus an square, and then error function of a1, error function of an. All of this is equal to 1 for the pi plus rank of the group generated by a1 square up to an square. So there's the additive group generated by this. That is what comes from the torus, plus the number of ai square such that ai is different from 0. That's the dimension of U. That's what the conjecture predicts. Now, these values here, so they are up to the square root of pi, they are values of an E function. And you can use, well, either Siegel-Shidlovskii direct or a nice work of Eric Tilleg to show that actually we have this here except for the 1. So the independence of these numbers with the square root of pi, that's the only thing we don't know. So what we know is that this is greater or equal than this whole expression without the 1, and the 1 is the missing thing. It's not too I should stop here. Thank you for your attention.